right, so I mentioned the on-demand processing, and I will go through the process of actually ordering, finding imagery, and then downloading it. After we go through the on-demand process in Vertex, we'll also take a look at some InSAR products in more depth. And then in the last few minutes of the session, I'd like to go over a time series approach for looking at interferometry. So I'm here at the Vertex data search portal. You can find it at search.asf.alaska.edu. And as I mentioned, this gives you access to all of the SAR data sets that ASF serves. There are a number of different ways to search for data. The default is to do a geographic search, but if you have a list of files that you want to look for, if you already know the file names, you can also just enter a list and search for those. And then there are the baseline and SBOS search types, which are for helping you determine suitable pairs for interferometry. I'll be going into those tools in detail later. And then there's the on-demand product search. So once you have submitted products for processing, those are available here. So you can search through all the things that you've processed in the past. So we're just going to take a look at this geographic search. By default, it looks for Sentinel-1 data. Again, you can search for other things if you're interested, but we'll start with Sentinel-1. The on-demand processing that we offer is only for Sentinel-1 data sets. So that's important to be aware of. If we just launch this search without setting any additional criteria, we come back with more than 14 million files. So it's important to kind of hone in on where it is you want to actually be looking. You can draw areas of interest in a number of ways. You can either just use the map, and the default is just to draw a square. You can also draw an irregularly shaped polygon, or drop a line or a point. You can edit your area of interest, just adjusting the position of the vertices, or you can also clear that area of interest if you want to start over. And you also have the option to import an area of interest. You can either use this button here in the tool or under the area of interest dropdown at the top. You can paste in well-known text of your area of interest, or you can search for files if you have a shape file. So I could just select the .shp file, or if there's a zip that includes all of the different components of the shape file, either of those are accepted. You can upload a GeoJSON or a KML. So if you already have an area of interest delineated, it's pretty easy to use that in the Vertex interface. There are also additional filters that you can set. So not just the area of interest, but also the date range, and additional filters such as the file type. So the list of file types available will be different depending on which data set you have selected. So these are the file types that are available for Sentinel-1. As I mentioned, the common ones that people download are the single look complex or the GRD. And you notice there are a number of different GRD options listed. Most of the time over land, the acquisitions will be in the GRD HD mode, which is a high resolution dual pol. But if you're interested in looking at ocean dynamics or sea ice, in some cases, those the ocean scenes are collected at in a different mode. Either it's a lower resolution, or it may just be a single pol acquisition. Also, in the older data sets, so if you're looking near the beginning of the Sentinel-1 mission, so 2014 and 2015, often they were only collected in a single polarization. So there may not be dual pol data sets available for those earlier data sets. So if you want to find everything, you can go ahead and click all of those different GRD options. Once you get more familiar with the data set, there are additional parameters that you can use to restrict your search even further. Now, because I'm logged in with my Earth data credentials, I can access my saved searches. So if you do a search and you want to have that saved in your profile for future reference, it's easy to do that. And then I can just launch one of these saved searches. So I'll open my search for the Ridgecrest area in California. There was an earthquake on the 4th of July in 2019. So I'll zoom to this search. And you can see that the saved search includes both the area of interest, which is shown here with the yellow bounding box, and also it shows all the footprints of the data sets that are available. The saved search includes any of the additional filters that I've applied. So in this case, I have selected the GRD HD and the SLC products and set a date range. If I click on any of the items in the results pane, the footprint for that product will be highlighted in red in the map. Or if there's a footprint that I really like on the map, I can just click on that directly and it will highlight one of the results that has that footprint in my results list. So this particular frame really covers my area nicely. The area that was impacted by the earthquake is nicely in the middle. And so I can restrict my search even further by using the more like this button at the bottom of the page. And that restricts the search further. You can see my search parameters are listed here, and it applies a path and frame filter along with all the other ones that I had set. So now only images that have that same footprint are displayed. So the earthquake took place on the 4th of July, and it actually happened not long after this acquisition. So if you are trying to create an interferometric pair for a very discrete event, like an earthquake where you have deformation caused by one specific thing that happens at one specific time, for your InSAR pair, you want to sandwich as closely as possible that event with acquisitions. So your before and after image ideally would be collected as soon as possible before and as soon as possible after that event. So as I mentioned, the on-demand processing is available for both RTC products and InSAR products. And if we look at this item here, there's just an option to submit an RTC job. I can either submit the SLC or the GRD. And if I submit my GRD, you can see that the on-demand queue has had an item added. Now, there's no InSAR option listed here. And that's because in order to process an InSAR pair, it needs a pair of images to give that interferometric output. So in order to find pairs, I have to launch either the baseline or the SBOS tool. Now, because I know that I want to use this particular image as one of my two images in my pair, it's easiest to use the baseline tool. So if I highlight this item in the results and click baseline, Vertex will open the baseline search type and populate the reference scene with that image that I selected. What we see is a plot that shows all of the potential images that could be used along with this reference scene to create a valid InSAR product. Now, you'll notice that there's this critical baseline. So only images that fall within the critical baseline are included in this plot. And essentially, so this perpendicular baseline on the y-axis, that indicates how far apart the acquisitions are in space. So where the satellite was in space when it acquired that image. And for interferometry, if you're looking at deformation, you want that perpendicular baseline to be as small as possible. So you want to be, if possible, acquiring those two images from the same place in space. If these acquisitions are too far apart, the phase decorrelates and you can't actually generate an InSAR image. So anything that's beyond that critical baseline, you can see there's nothing up here that's listed as an option for generating an InSAR product. So I'll zoom into this area. Again, this indicates my reference scene. So that's that July 4th date. And so the next acquisition was 12 days later. And the acquisition, the perpendicular baseline was 30 meters apart. So if I click on that item, it's highlighted in the results list. And again, it shows me that it's a 30-meter difference between my reference granule and that one in terms of where it was acquired, and it's 12 days apart. So I can click the on-demand icon, and now the InSAR option is available to me. So I'll go ahead and add this one SLC pair to my on-demand queue, and you can see now I have 2 products listed. So if I look at some of the other acquisitions that were acquired after the earthquake event, there's this one here that was 36 days later, but it's extremely close in terms of where it was acquired in space. So when you're choosing what your temporal and perpendicular baselines should be, it can depend on your particular situation. So in some places, if it's a fairly stable environment other than that deformation, it may be okay to have a longer temporal baseline, and you can choose then that the narrower perpendicular baseline to get that tighter correlation of the phase values. But in some cases, in 30 days, a lot of things could change. For example, in areas that have really rapid vegetation growth in that time period, that could change the phase measurements. And so you could be muddying the signal that's being returned from that deformation by other things that are going on that are not related to that deformation. But I'm going to go ahead and add this pair as well, just so that I can compare the results from that 12-day interferogram and the 36-day interferogram. So I'll add that to my list. I also have the option of adding RTC products from this place as well. So if I wanted to have an RTC product for that 12-day acquisition, I can also just click the on-demand from here and add one SLC job. You'll notice that the GRD option is no longer available, because once we launch the baseline or the SBOS tool, that's for interferometric purposes. And so only SLC products are valid. And so the search is restricted so that it only includes SLCs. So in this, if you wanted to select this one and process the GRD, you'd have to go back to the geographic search and find this one and add it from there. But I'll go ahead and add the SLC job for processing to RTC. And at this point, I'll click on my on-demand button here and open my on-demand queue. Here I have a tab for the RTC products and the InSAR products as well. And each one of them provides different options for processing. So if you want to learn more about each one, you can just hover over that item and it gives a little bit more of a description. If you want to go a little bit more into the details, I again recommend that you look at the product guide under the HYPE documentation, which goes into the impacts of some of these different choices. So for RTC, I have the choice to process either to gamma naught or sigma naught radiometry, power or amplitude scale. And again, I can choose to use either the Copernicus DEM, which is the default and what we recommend, or if you do want to use the legacy DEM, that is also available. There are a number of processing options and then a number of optional items that you can choose to include if you want to do some higher level processing that requires some of these additional data sets that most people don't need. I'm going to choose to include the RGB decomposition image. This is a GeoTIFF that combines the VV and the VH polarizations into a color decomposition. Now I'll take a look at my InSAR options. So the number of looks will drive the pixel spacing of the output product. So if I choose 20 by 4, my output product will have a pixel spacing of 80 meters, which in most cases is going to be sufficient. If you choose the 10 by 2, that gives you a 40 meter resolution or pixel spacing image, and it's a much larger data file, so it's a little bit more cumbersome to work with. But if you do require that higher resolution, then you can choose this option instead. But just be aware that when you do that, it takes longer to process, but it also is more cumbersome to deal with. You can choose to include the digital elevation model and a number of other optional files. I'll choose to include the displacement maps and the wrap phase GeoTIFF. And I'm now ready to submit my jobs. So when I'm about to submit these jobs for processing, if I decide that I'm not ready to submit my RTC jobs, I can just uncheck one of the box that I don't want to actually submit. Same thing with the InSAR. But if I'm ready to submit them all, I can leave them both checked and enter a project name. I can enter something completely new, or I can reuse a project name that I already have established. So I have one for Ridgecrest, and I'm going to add these products to this same project name. I'll submit my jobs, and you can see there's a notification here that tells me my jobs have been submitted. I can click on this notification to look at those on-demand products, but I can also use this on-demand button and click on the submitted products option, or I can just select on-demand products for the search type. So there are many ways to get to your data. Once the jobs have been submitted, you can see that they have a pending status. This will shortly change to running. And then once those jobs are complete, which again for RTC, we usually expect it to be about half an hour. And for the InSAR jobs, it's usually about an hour. So if I come back, I'll see that there are zip files available for download. So once the products are complete, you can click on an item and download that to your computer. There are options to filter these results. And so I'm just going to look for this Ridgecrest product that I just submitted to. So you can see that I have some products from before, my pending products, and then I have some old products that are actually expired. So when you use on-demand processing, the products are available for 14 days after you submit the job. And if you don't download it in that time, it's still listed. Well, regardless of whether you download it or not, after 14 days, that product is still listed in your list, but you can't actually download it. It doesn't actually exist anymore. But if you want to reprocess that, say you forgot to download it and you want to reprocess it with the exact same parameters that you applied the first time, you can just click on the expired button and click resubmit, and that will just fire off a job right away that will be added to that same project name. It'll have all the same parameters as the first time you processed. If you have one that you want to resubmit, but you want to actually change the parameters or add it to a different project name, you can just click on the on-demand option and you can add that pair, and that will add it into your on-demand queue, just like we did before when searching for new data. And you can go in and submit it just like you would with any other job, where you select the parameters, you select the project name, and carry on to submit that job. So if you have a lot of expired products and they're sort of distracting, you can choose to just click the button to hide those expired products so that they're not cluttering up your space. And again, if you want to download products, you can either do them one at a time by clicking this download file icon, which will just launch the download directly in your browser, or you can add it to your cart, and then you'll have an item in your download cart if you wanted to go through and add a whole bunch of things at once. I also have the option, if all of these products that are displayed that have valid zip files, if I want to download all of them, I can just click this queue button at the top of the list and add those to my downloads queue. Now to download in a bulk way, I can open this queue and either go ahead and just download each one of them individually, or under the data download option, there is this item to download a Python script. And so if you have Python installed on your computer and on your path, you can download this script and just launch it. It will prompt you for your Earth data login credentials. So it asks me for my username and password, and then it carries on to download each one of the items in my download queue one at a time. All right, so this approach for using the baseline tool to generate InSAR products is good if you know exactly the pairs that you want, or if you want a very specific set of pairs processed to InSAR. But in some cases, you may be monitoring something that's more long-term. So like this earthquake, for example, that was a discrete event. So it happened, there's deformation, and I just want to look at that very specific event. But there are some things that happen over longer time periods. So things like volcanic dynamics, where you may have inflation of a magma chamber that raises the ground and maybe deflates after a while, or if there's an eruption, there are changes that occur. Or if you're looking at subsidence due to groundwater extraction, or some of these longer processes where you can't just capture in one short time period the motion that's going on. It may be very slow movement that requires a longer time interval. If you could just do an annual interferogram, for example, or a longer interval for your InSAR product, and so say, oh, I'm going to do an interferogram from January 2017 to January 2018, and that's valid in some cases, but you have to keep in mind that there are things that change the Earth's surface in terms of the phase measurements beyond just deformation. So it's true, there may be deformation occurring in that year, but there may also be vegetation growth, or maybe there are changes in soil moisture or in other surface conditions that impact the phase measurements. So if you're relying on long interval interferograms, you have to be aware that you're integrating things other than just displacement. So if you want to look at a long process, but minimize the impacts of those long intervals in your interferogram, you may wish to use a time series approach. And the SBOS approach uses a time series of very short baseline interferograms. So they're close together in time, but they cover a long period of time, and they overlap different intervals in that time period. So you might have a 12-day interferogram and a 24-day interferogram that cover the same time period. So if you're interested in that time series approach, let's look at launch another save search over the Fernandina Island, which has a big volcano. It's in the Galapagos, just off the coast of Ecuador. And if I want to do, so this volcano here is very active, and it inflates, it deflates, it erupts and changes. There's a lot of activity going on. And so it's a great use case for doing a time series analysis. So if I select, again, a reference scene that covers my area of interest nicely, I can launch the SBOS tool rather than the baseline tool in order to look at a series of pairs. So I've selected this image, which has this nice footprint. I'll launch the SBOS search, which again sends me to this SBOS search type and populates my reference scene with that reference image. And my plot looks a little different than the baseline plot. Essentially, this shows every single pair over this area since the beginning of Sentinel-1 time. Now that's 3,700 pairs. That's a lot of data, and maybe not all necessary for what I'm interested in. So the first thing I'm going to do is restrict my date range so that I'll click this SBOS criteria button and set my start date to be 2017. So I'll start on January 1st, 2017. And then for my end date, I'll set that to be May 1st, 2020. So I'll apply that to my search. And if I zoom in here, I can see that my pairs are a little bit restricted. Each one of these points indicates an acquisition, and each one of the lines in between the points shows an InSAR pair. So I've got a whole bunch of these pairs, and there's more data that was collected starting at the end of 2018. So there's a very dense time series for interferograms in the more recent part of this time series. So I'm still at 2,000 pairs. I can reduce that further by setting my perpendicular baseline to have limitations. So if I only want acquisitions that are more like 100 meters apart in their perpendicular baseline, and I can also change my temporal baseline so that I only have, acquisitions that are less than 25 days apart. So this has restricted my timeline, my time series a bit further. So I'm now down to about 1,000 pairs. In this area, there's probably not a lot of seasonal impact, like there's not a strong seasonality. But if I was doing a time series analysis in Alaska, for example, the conditions in the winter would be very different than the conditions in the summer. So if I was generating interferograms that spanned seasons, it may be confusing what I'm actually trying to look at. So in some cases, I might want to restrict my search to a seasonal search. So I'm only looking at data that's acquired in the snow-free season, for example, because snow cover and freeze conditions, soil, like if the soil is frozen or differences in soil moisture will all impact phase measurements. And so in some cases, I might want to keep that more consistent. So I can apply a seasonal search and set it so that I'm just looking at data within the snow-free period in Alaska. So I'll apply that search, and you can see that now my results are restricted to just that seasonal time period. So when you're doing seasonal analysis in a time series approach, it can be a problem to have these gaps. And so you might want to bridge the gaps with an annual interferogram. So in some cases, the annual interferogram is a better choice than something that spans seasons, because even though there are other things going on, the conditions are more similar. Like a July image compared with a July image is going to be more similar than a December image compared with a May image. So for bridging these gaps, you might want to add an annual interferogram. And I can do that by clicking this custom pair option, click the plus button, and I'll select this date here, which is July 6th in 2017. And then here's an acquisition from July 27th, 2018. And I'll add that to my queue. So that's been added to the bottom of my list. And I'll add another pair then, bridging the next year from July 7th to July 8th, 2019. And that's also been added to my list. So now I've got a list of 240 pairs that I could use for my time series analysis. I can explore each one of these and add individual pairs or individual RTC jobs to my queue. Or if I'm happy with my entire list, I can choose to select the on-demand button at the top of the list and add all 240 pairs to my on-demand queue. Similarly, for RTC, I can go through and add very specific pairs of jobs for RTC analysis, or if I want to have an RTC product for each one of the acquisition dates, I can also add all of those jobs to my on-demand queue all at once. And that is how you would generate a time series of interferograms. So once processed, you'd have 300 interferograms to work with in a time series approach. And at the very end of this tutorial, I'll go through how you might want to work with that data. But for now, let's take a look at some of these InSAR products, the individual pairs that we processed. So I've downloaded these to my computer and extracted them. And I have these RTC products that have an RTC in the file name, and then the interferograms have an INT in the file name. This is my 12-day interferogram, which ranged from the 4th of July to the 16th of July. And then this is the 36-day interferogram, which ranges from the 4th of July to the 9th of August. So if I expand this, you can see there are all these different products that I mentioned, including that README file that you can open and explore the data sets a little bit more. And if I click the option to view the metadata, then this gives me access to that XML file that has all the specific information for that particular raster. So let's look first at the color phase browse image. So this is actually a lower resolution product that's included, and there's this color fringe that's applied that's based on a 2π scale. So when you're measuring the phase differences from one acquisition to the next, all you can truly measure is the difference within the phase cycle. You don't know which multiple of that phase cycle the return is in. So it could be 3 phase cycles plus a little bit, or 2 phase cycles plus a little bit, and those would all look the same in terms of the value in the wrapped interferogram. So the wrapped interferograms range from a pixel value of -π to +π. So this colorized version of that gives you that visual cue in terms of where the most deformation has occurred. So in this case, this was the fault, was right along the center part of the interferogram. And there's high deformation right around the fault, but then things are pretty stable. There's not much change going on at the edges of the image. So if we look at these fringes, so say I was to start at this pink fringe here on the edge. So this is kind of beyond where most of the deformation has taken place. So if I count fringes inwards, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, about 24 fringes to get to this little spot here that seems to be sort of in the middle of things. So if I wanted to calculate the line of sight displacement, I can use the wavelength of the sensor. So for Sentinel-1, that's 5.6 centimeters approximately. So I'll put in 0.056 meters and then divide that by 2. And then I can multiply that by the number of fringes that I counted. So I counted 24 fringes. And so the amount in the line of sight of the sensor of displacement that I would expect from this spot here, that kind of beyond the main deformation, to this spot here would be close to 0.7 meters. And we'll take a look at other ways to calculate that in a moment. But we'll just, let's take a look at the actual TIFF image. So that browse image doesn't have any values associated with it. But if you wanted to look at the actual wrapped phase values, you can look at the GeoTIFF. Again, that ranges from -π to +π. So if I zoom into one of the black areas of the fringe, the value is close to -π. Whereas in the white part, it's closer to +π. So -3.10 versus +3.03, etc. So I can see that these are those wrapped fringes. And if you want to count, that's fine. We could do that manual thing that we just did to calculate the line of sight displacement. But I have to say, this is sort of a poster child interferogram. They're not all quite this clear. So it may be much more difficult in some cases to count those fringes and figure out what's happening or how the movement occurs across the image. And so there are algorithms that do that phase unwrapping for you. So basically it starts at the edge of the image and moves in. And for each one of these subsequent fringes, it multiplies the subsequent integer. So rather than having 2π, 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 it will be 2π, 4π, 6π, 8π, 10π, and onwards. And that phase unwrapping algorithm does that automatically and takes into account if there are discontinuities, and has it's a much more kind of complex process than me going in and finding a pathway to count the fringes. Because as I said, many images, the fringe pattern is not quite this distinctive. So in our case, to do phase unwrapping, you need to define a reference point, and that's where you're going to start from and adding those multipliers to each subsequent fringe. So for our purposes, we can't go in and define a reference point for each individual interferogram because we're doing this automatically. There has to be some automated reference point chosen. And so for our on-demand products, we use the first point where both pairs are imaged as the satellite is moving along. So this is a descending image. So the satellite is moving downwards along this path. And so the first item, the first pixel that would have been imaged in this particular case is the upper right corner. So that would be the reference pixel for phase unwrapping. If there's an ascending scene, it's the opposite. So the sensor is moving along this way. So the first pixel that would be encountered would be in the bottom left corner, and that would be the reference point for phase unwrapping. So let's take a look at what happens when you unwrap that phase. So that changes the cyclical approach to measuring the phase differences to a continuous ramp of values. If I look at, I'm just going to overlay the fringe pattern again. So if I look on the edge of the image where I would assume that there's not much deformation, that the fringes are very wide apart. If I click on this yellow fringe that's near the start of the phase unwrapping, you can see that the wrapped and unwrapped phase values are exactly the same. This is all in that first cycle of the fringe. So no multiplier has been added on. And it's close to -2 for the yellow fringe. If I move inwards and choose a yellow fringe that's closer to the action, the wrapped phase value is still close to -2, but the unwrapped value is now -21. And if I move even closer, so this yellow fringe, again, wrapped is close to -2, whereas unwrapped is -71, and so on until you get very close to the action, where we see something like -139 for the phase difference for the unwrapped image. So the unwrapped image is then used to generate displacement maps, which are an optional product that you can add into your InSAR product. And these displacement maps convert the phase difference into the actual displacement in meters. So it essentially applies that same calculation that I did manually. And so if we look at the line of sight displacement here, the values have the opposite sign. So here's the unwrapped phase, it's a -105 pi radians. And then in the line of sight displacement, that's converted to positive 0.46 meters. And this sign difference is due to the fact that the phase difference is calculated based on the reference of the sensor. So it's relative to the sensor itself. So if you have uplift of the ground, the ground is closer to the sensor. So the distance traveled by the signal is less the second time than the first time. So you get that negative phase difference. Whereas in an area that you have uplift or subsidence, the Earth's surface is actually further away from the sensor. So the signal has to travel longer. So the phase is further along. So you get a positive phase difference. But if you're thinking in terms of the deformation of the Earth, that's sort of an unintuitive way to think about uplift and subsidence. So in the displacement maps, we use the convention of having it relative to the Earth. So in the line of sight displacement, that is movement towards the sensor would be uplift, which is a negative phase difference, but that's a positive change in the Earth's height. And so that's why we use that positive value for the displacement. It's important to be aware that this is not a universal convention. So if you're looking at interferometry products from a variety of sources, you need to make sure that you're understanding which signal, which sign they're using. So in some cases, some programs may not flip it in that way. It could be it's still relative to the SAR sensor. So be sure that you're aware of that signal direction. Otherwise, you could be mixing up your image and thinking that there's uplift where it's subsidence and the other way around. Now, as I mentioned, this particular image is sort of a poster child in terms of the phase unwrapping. We had the default reference point was in a great spot. It was basically you want it in an area that is not undergoing deformation and that has high coherence, which happens to be the case for this particular image. So the line of sight measurements are probably fine. But if this deformation was over in this corner where the phase unwrapping began, you may have a scenario that the phase unwrapping begins partway through the deformation. And so it might not be capturing kind of that whole movement. And you can correct for that by choosing your own reference point that's in an area that you trust. It's in a region where you would expect little deformation and where there is high coherence. So you could choose a point, say over here, and then look at the value based on the default reference point and just subtract that from the image. So that would apply that correction to the entire image so that you would be capturing the full line of sight displacement from that new point rather than from the midway point of the deformation. So we also have that 36-day interferogram, and I want to do a quick comparison of those products. So here we have the color phase for the 36-day, and let's just toggle between that and the original one, which is the 12-day interferogram. And while there are some slight differences, overall, it's quite a similar image. If you look at the fringe patterns, oops, sorry, wrong one. If you look at the fringe patterns, they're quite similar. And if you compare the line of sight displacement values of the two images, they are quite similar. So the 36-day and the 12-day interferograms are in pretty good agreement. And this is reassuring on a number of levels. First of all, it's always a little bit perilous to make decisions or come to conclusions based on a single interferogram, because as I've mentioned, there are things that can impact the phase measurements other than just deformation. So if, for example, you had different atmospheric conditions during the two different acquisitions, that can also impact the phase differencing, and it can make it look like there's deformation that's not there. So while SAR can image through clouds, it's not unaffected. So most of that backscatter will come back to be measured, but the phase can be delayed if there's a lot of water vapor in the atmosphere. So even though the signal comes back and you can see that image, it takes a little bit longer. And what we're interested in interferometry is the phase part. And so if you have a delay that's caused by water vapor, it takes longer, which is the same thing that happens when the ground moves away. So you can mistake atmospheric impacts for deformation. So by comparing interferograms that have different acquisition dates, that can help you determine if what you're seeing is a consistent result or if there may be atmospheric impacts involved. If you do have atmospheric impacts in your images, you can apply a correction using an atmospheric model or a time series approach that sort of smooths out those impacts of individual strange anomalies based on an unusual water vapor content compared to all the other images that you're using. So by having these two interferograms that I can compare, the fact that they are so similar gives me more confidence that I don't have other things going on that are impacting those phase measurements. So at this point, I'd like to do just a really quick demonstration of how you might use a time series analysis to look at data. So here I have a Jupyter notebook that uses an algorithm in MintPy, which is a open source time series software package. It's a Python package that's openly available, and it's designed for working with large time series data sets. So if you do an SBOS time series and you've got this series of interferograms, it's a lot of data to consider and process. And so this is one of the packages that is commonly used to synthesize all that data together into a more understandable output. In the last slide of my presentation, I've listed links to the MintPy software packages. They also have a number of Jupyter Notebook tutorials. And there's also an area in their documentation that is specific to using HYPE generated data sets. So our on-demand products can be used in MintPy. And we're working on a notebook that gives a pretty seamless workflow for taking HYPE produced data and generating a time series output using MintPy. That's still in development, but definitely check it out. It's something that we're actively working on to make the experience even easier. So I've run this small baseline application and on a stack of InSAR products that I've generated with HYPE. And I have this visualization portion of the output. So here we have an image of that Fernandina Island that has the volcano kind of in the middle. And I can click on acquisitions through time to look at the deformation or the displacement that's happened on the island at particular time periods. So things are fairly stable in 2015 and 2016, but then you can see that there's some inflation occurring in the latter half of 2016. And then as we approach, there's an eruption that actually takes place in September of 2017. And you can see that displacement pattern really changes after the eruption. And then the volcano actually continues to inflate over time until there was another eruption. The last image in this acquisition, actually, you can see that the displacement pattern really changed after that most recent eruption in the time series. So this is looking at 100 InSAR products and distilling it down into just one picture that you can explore interactively and get kind of those visual understanding of what's going on. You can also click on a pixel and it will display the displacement at that particular point. So around the edge of the island, there's not too much going on. Things are pretty stable. But if I click on this pixel right in the middle of the crater, you can see there's clearly something else happening. And so you had this slow inflation in 2015 and 16. And then there's a little bit of activity here at the end of September during that, or at the end of 2017 during the September eruption. And then it continues a rapid inflation until that eruption at the end of the time series in this example. So this is a really powerful way to take all of that information that's just huge amounts of data and distill it down into an image that's easy to understand and explore. And with that, we have a little bit of time for questions. I know I've covered a ton of information. Again, this recording will be available on the website that we linked in the chat, and the presentation with the reference slide for all of the resources that are that I've mentioned in this tutorial are there. But if you have any questions, we can take a few minutes to address those.